它有过什么证的？对，不是这样，愿意的。他们那边不懂，就是完全每个
Okay, anybody have any questions before we get started? So today we are going to finish our discussion on Riemannian geometry. So what are distances on manifolds? That's our goal for today. If you look on the schedule, I mentioned the upcoming topics last time are going to be shape and representing shape on manifolds, and then how we do statistical analyses on those types of manifolds. How do we define things like taking averages on manifolds? That's going to be the topics next week. We might get started with the intro of shape manifolds today if we finish geodesics quickly enough. Before the end class, I expect we'll probably at least get started with that. Aman will be back on next week for our rotating teaching. And let's see. Oh yeah, then on the schedule, there's some reading material for next week on the shape stuff and the statistics on manifolds. And if you see, I think the next topic with shape manifolds will be a specific shape space called Kendall shape space, and it's named after the guy who invented it, David Kendall. And so the paper there is the original David Kendall paper from like the early 80s, I think. And you don't have to read it in every gory detail. It's like some ridiculously long paper, like 30 pages or something. So don't feel like you have to read that carefully. It's there for kind of reference. We'll go over the whole construction of that shape space mathematically, and how to compute things on it on Tuesday. But if you want to kind of get a sense of the original paper, it's there for reference. Okay. The other thing is homework 2 is not yet posted, but will be shortly. I'll send an announcement by email. I'm planning to post it today, I think, if I can get that done this afternoon before I go home. So look for an email, and it's going to be a couple of things you have to do there. One is going to be, you'll have plenty of time for this one, and we'll talk more about it as we go next week. But the first thing you'll do is compute the geodesic equation, which is what we're doing today in class, specifically on the sphere, the true sphere. And then the next thing you're going to do is some basic statistics on Kendall shape space, computing statistical analysis of some shape data. So the first kind of data analysis in the class will be in this homework. Okay, so yeah, that's kind of what's happening on the schedule. Any questions about any logistics? Okay. So we'll go ahead and get started then. So yeah, so let's just review what we talked about at the end of last lecture. We were talking about what is a Riemannian metric and a Riemannian manifold with a Riemannian is a manifold with which has a Riemannian metric. So what is that metric? I'll just kind of review that. Just remember, I'll draw a picture again. Our usual manifold M here. And at a point P, we have a vector space called the tangent space, dPm. And again, if M is an n-dimensional manifold, this is an n-dimensional vector space, which we talked about kind of how I can write down this vectors in this vector space in a basis, and that they are differential operators. But what we're talking about with metrics is now adding one more piece of structure to this tangent space, and that's an inner product. Because without the metric, there's no notion of dot product angles between vectors, and there's no notion of how long a vector is. There's no norm. I just have an abstract vector space with no other structure. So to get things like what's the angle between two vectors, what's the length of a vector, you need a dot product or inner product. Okay, so if I give you two vectors UV in my tangent space, a Riemannian metric is that's an inner product. At each point P, and I should say an inner product at each point P, the inner product is on the vector space, dPm. And again, inner product just means I give you two vectors as inputs. I take the dot product, and again, we'll often put a subscript just to indicate that we are in a very specific place in the manifold. And remember, this has to be, the rules here are, I'll just write this ABC here. This has to be bilinear. So that means linear U, linear V. It has to be symmetric, meaning I can flip U and V. I can do V dot U, U dot V. I get the same number. And the last thing is it has to be positive definite. Which, remember, means that any non-zero vector, one way to say it is that any non-zero vector has a positive length under this norm, which I can write is that the norm, and I'll just put a square on it, the norm squared of U, which is defined as U dotted with itself. Again, I'll put a P here just because this is that point, is greater than 0 whenever U is a non-zero vector. The zero vector always, sorry for the zoom camera, the zero vector always has zero norm. By the bilinearity property, you'll end up with a zero norm. But if you give it a non-zero vector, that has to be a strictly positive length for that vector, or square length, way I'm writing it here. Okay. That was just the definition of what's an inner product on a vector space. Now, for this to all make sense on a manifold, at every point property needs to work nicely with the differentiable structure I've defined on my manifold M. And by that, what we mean is that the inner product changes smoothly. The inner product changes smoothly with position P. I'll just write this in words, but kind of come back to it in a minute here. The inner product changes smoothly with position P. And this is a very loose way of saying it, changing. What do you mean by changing smoothly? You mean that if I write things down in a coordinate system, so I've got some open set U, which contains P, and that open set has a chart. X gives me coordinates. And again, remember, we're going to do superscripts for the which dimension you're in and the coordinates. So x1 is the first dimension coordinate, x2 is the second dimensional coordinate, etc. And then I write tangent vectors down here in this space, u and v. And again, this is an abusive notation. U and v really live in this space, but I can think of it as living also in this space, kind of like simultaneously, because it is, one-to-one bijective smooth map going back and forth here. This coordinate chart. So things really live in both places simultaneously for all intents and purposes. We can abuse that notation that way. And remember that when I have vectors in a coordinate system, I can write them in the basis that coordinate system induces on the tangent space. And that basis is the coordinate vectors are the partial derivative operators, ddx1, ddx2, out to ddxn, so forth and so on. At this point here, the standard basis and tangent space units are going to be this. Okay, and then any vector I can write in this coordinate system. And over here. So I can write B and that. I can write U the same way. Okay. And then any inner product, if I think of it again as Euclidean vector space, or sorry, don't think of it Euclidean. It's a vector as a vector space with a basis, I should say. Then I can always write a dot product, and by dot product I mean, or inner product, I mean a thing that satisfies these three rules. And this is all just linear algebra here. There's no manifold stuff. Just I'll do linear algebra when I'm in the tangent space. To satisfy these three rules, this inner product operation, it has to look like, again, in a basis, V transpose GU, where G is a symmetric positive definite matrix. So remember, symmetric means G is the same as G transpose. Positive definite means greater than 0 eigenvalues. All eigenvalues are greater than 0. Okay, and again, I'm kind of now writing things as we typically write in linear algebra with transposes and vectors and matrices. But this equation is really assuming I've written this down as like a column vectors in an n by n matrix, but that means I've put it into some basis, and the basis I've put it into are this coordinate system, the x ddxi partial derivative basis here. Okay, so like we said last time, G in this same xi basis is going to just be a set of n by n values. And of course, because it's symmetric, you know, the top triangular part is the same thing as the reflected bottom triangular part, lower triangular part. That's this Gij is Gji, of course. What we mean by G is G transpose. So it's really just n choose 2 unique values here, not really n squared full unique values. Okay, so that's what satisfies those linear algebra properties is any matrix that's symmetric positive definite. You give me 2 vectors, and I'll have an inner product that's bilinear, symmetric, and positive definite. So that's what I need this G to be. Now the part 2 to be a Riemannian metric, I need G to change smoothly. And all that means is that really all of it, of course, is varying with X. If I'm in this neighborhood and I've got this X coordinate system, and that P here, right? If I move to some other coordinates and I get another point close by, I'm just changing my X's. And if I change my X's, the G can change because it has a different, I have a different inner product in every tangent space. So now I'm going to think of these Gij's are really functions of X, which I'll write it out as the whole set of coordinates. Okay, so each of these n choose 2, you know, roughly half a matrix of values are going to be functions of these n coordinates in my coordinate system. And what I need is that each of these functions are going to have to be smooth functions for all possible ij's here. So each entry here in this matrix is just a smooth function if I write it in any coordinate system. So I should have said this has to hold for any coordinate system X. I pick a different coordinate system, I'll get a different matrix here, but it'll be equivalent to this matrix if I change the coordinate system. I've changed the matrix, but I also changed the basis that U and V are written in. I'll get the same number. Everything will just be a change of variables. Okay, so that's a Riemannian metric. And so yeah, it's you know, bottom line, it's just those 2 things. It's an inner product, and the inner product, if I'm writing a coordinate system, is a bunch of smooth functions that changes smoothly. And I'm going to just use the word smooth, by the way. I know we've been saying like C1, C2, CK or whatever. I'm just going to say the word smooth, typically meaning C infinite, but you know, you could also replace this with C1 in this case, but it's the amount of differentiability is not super critical for what we're doing here, but we'll just say it's differentiable. Okay. Any questions on Riemannian? What's a Riemannian metric? Okay. And now we can get back to the question, we started with lecture last time, but did not answer, is how do I find shortest paths? Really, we're going to be interested on a general manifold. If I have a Riemannian metric, how can I compute the length of a path? And then how can I find, and just give me the endpoints, what the shortest path is between those 2 points. And as a special case, because we know Euclidean space is a manifold, and the metric, if I'm just in just a standard basis, would just be the identity function, the identity matrix everywhere in Euclidean space. That gives you a Riemannian metric, which gives you the usual Euclidean metric that we're used to, where straight lines are the shortest paths. Those are geodesics. That would be a special case of the more general geodesic equation we come up with here today. And we'll see mathematically that yes, straight lines are the shortest paths between 2 points. But right, we're going to do the manifold case. I'll have a P and a Q, let's say. And if I give you a path there, first of all, let's just say this path already, let's call this gamma. We can figure out how to write down the length of this path, because we've got the notion, as we talked about last time, we've now got the velocity of this path. I can talk about the length of that velocity, so I can write down the same equation for the length of this curve that I write down in multivariate calculus for the length of a curve, space curve or plane curve. I would just, if gamma, let's just say gamma is a curve that maps the interval AB on a real line to my manifold, and again, it's got to be a differentiable curve, at least C1, one times differentiable. Then I'm going to integrate along time, the time interval I have here, the norm of the derivative of gamma, and that gives me the length of gamma. I'm using, of course, the notation gamma prime is gamma dt. Of course, as we do in usual calculus as well. And notice that derivative of gamma, that velocity of gamma, is a tangent vector. And this norm is, I could put a subscript here, it's being evaluated at whatever tangent space we're at gamma t, that's the position. I could put a little gamma of t down here. I usually would leave that out because it just clutters up the notation. This norm is not a fixed norm, is the point. It depends on where you are in the manifold. But we have that norm as the dot product of this with itself and then square root. Okay, so this is a thing we can calculate now. If you give me a Riemannian metric, I can calculate the length of any curve you want. Okay, now of course I have to have an equation, a concrete manifold with equations I can write down. I can write down that metric, but if I had that, this equation would be computable, is the point. Okay. Now, the kind of thing we want to do is we want to take a argmin, if you will, over all possible curves. We want to minimize, and we'll call this, let me just call this like gamma hat. Gamma hat is our shortest length curve. If we could do this minimization problem, search for the shortest possible, the thing that minimizes gamma, it minimizes L of gamma. And I should say we need to search over curves such that, you know, the start point is P and the end point is Q. We're only interested in curves that start at P and end at Q. So we're just going to have curves that look like this somehow. And we're gonna just look over all possible curves and find the shortest one. Okay? That's the idea. But how do I do this? This is not, searching over the space of all possible like differentiable curves between 2 points. It's obviously it's actually an infinite dimensional space, not just a continuous space, it's an infinite dimensional space. And it's not something I can just wander around and get lucky. So I have to do what's called calculus of variations, which is essentially calculus in infinite dimensions. So if I think of gamma as living in a space, it's not living in like a multivariate vector space, that's multivariate calculus. Gamma really has infinite degrees of freedom. If you think about all ways you can move a curve, there's infinite dimensions to move in, and you're in an infinite dimensional space. The details of which are beyond the scope of this class. You have to put some structure on the space of curves, but we can think of it as an infinite dimensional vector space is the bottom line. Now, typically, we can see what we're going to do here without resorting to infinite dimensional calculus explicitly. So we're not going to have to do that explicitly. We can think of it actually boiling down to just 2 dimensions in the following way. So I'm going to redraw that picture. I've got P and Q, and I've got gamma going between P and Q. I'm going to kind of put the label out here because I'm going to need to draw more here. Okay, and gamma, of course, has a parameter T, just a real value parameter T. That takes me from P to Q, right? And what we're going to do is we're going to create what's called a variation of gamma. So think of taking gamma and just perturbing it. So I'm just going to, make a little infinitesimal perturbation and get another curve. That's just a small perturbation of gamma. Okay. And what we want is, if you think about this perturbation as like a derivative, okay, like if I'm a point in Euclidean space and I perturb that point and I see how something changes, a function changes, right? That's as we talk about, that's like taking a derivative, perturbing the input and seeing how the output changes. And so L of gamma is like a function on curves. So I'm going to perturb the input of L and see how the output changes. That's what we're doing. So in a sense, trying to take a derivative of L, the length functional. And we know that functions are minimized when they have 0 derivative, right? And so this perturbation of gamma, if I'm at a 0 derivative of L, I would like to be at a 0 derivative because that means I could be technically a minimum, a maximum, or a saddle point. It turns out you can show it's a minimum, which we won't get into. But that's the goal, is to show that this perturbation is like a 0 derivative of L. Okay. So how do we do that? Let me pause and see if anybody has any questions before I get. So this is not actual legitimate math, but let me write down just an analogy here. So you can imagine if I thought of calculus as gamma as a vector, and I'm doing multivariate calculus, what would I do here? I would say plus epsilon times this perturbation. So let me give this perturbation a name, eta. And epsilon is just a scalar, like how much am I pushing gamma in that perturbation? And this is not valid for manifolds, because I'm taking a manifold value and adding another thing to it, which we don't have addition on a manifold. So this only makes sense for vector spaces, but it's an analogy that we can take here in a minute. I could then take the derivative of this with respect to epsilon, right, and evaluate that at epsilon equals 0. If again, gamma was a vector, eta was a vector, and epsilon was a number that I'm taking a derivative with. So this is how I could talk about a perturbation of a vector. Like I would perturb a vector if this were gamma, this were eta. I could perturb the vector, which is the input my L function, and then take a derivative of what's the change of L as I perturb it that way. Okay, so this is the analogy of what we're doing. This is an analogy, just to be clear. This is not exactly mathematically valid for what we're doing in manifolds, but this is an analogy if this is all in Rn and not curves on a manifold. Okay. And this, if this were equal to 0, then notice this is a directional derivative in the eta direction. So I'm saying that if this evaluates to 0, then L has a 0 directional derivative. But what I really want it to have is a 0 no matter what direction you go in, right? Like if you think in 2D, if I was in 2D and I had a function, let's say I'm drawing as a height function above here, something like this, I want to be a 0 derivative kind of in all possible directions in the plane from there, meaning that like if I look at the level sets, this is a valley and I've hit the rock bottom of the valley. That means in whatever direction I go in, the directional derivative should be 0 at that point. The gradient of that function should be 0 at that point. Okay, so it doesn't suffice to just look at one perturbation of gamma. I have to say for all possible perturbations eta of this curve gamma, no matter how you perturb it, at least infinitesimally, that the length functional derivative of that perturbation will be 0. So that's kind of, again, the way to think if you think about functions in vector spaces and how you talk about minima of a function, a multivariate function. We're now thinking of L as a infinite variate function where the inputs are curves, but the same principles apply that to be a minima, I need all the possible directional derivatives, all perturbations of this input to give me 0 derivatives. Okay. Any questions? All right, so let's how do we set that up? What we're going to do is, like I said, we're going to do a so now this is the analogy right here. Now how do we do this for curves on a manifold? We're going to do a variational, or I should say a variation on gamma. And what does that mean? We're going to make a function alpha, which goes from 2 real numbers to the manifold. And the AB interval is going to be the same interval that gamma. I really should say this should be closed, sorry. Doesn't matter. Super. But this is the same interval that gamma was defined over for T. Okay. And this is a new variable, and I'm just going to go around 0 minus epsilon to epsilon, where epsilon can be just some small number, and I'm going to call this S. Okay, so now I've got a pair of parameters for alpha, one of which is the same time parameter that I was using for gamma. The output will just be, again, a manifold, a point on my manifold. So now what does alpha look like? Actually, let me give you some more rules here. Alpha has to be smooth. And again, depending on what derivatives you're doing, first derivatives, second derivatives. It needs to be at least first derivatives. So alpha is smooth as a function of both s and t. I want it to be the case that when s is 0, but I can vary the t parameter, that's the same thing as gamma of t. And then I want it to be the case that the endpoints of t at A and B are always P and Q. So if I vary S, but I keep the T fixed at A, I always get P. And if I vary the S for whatever you want, but fix the endpoint at T equals B, I will stay at Q. Okay. And what does this mean? Let's again draw. I guess I'll just redraw this. P, Q. I've got gamma. I'm going to kind of draw as a thick curve now. So that's gamma. Again. And alpha is going to be this kind of two-dimensional coordinates which emanate from gamma, like so. And let me make some more labels here. Again, I'm going from the ST kind of rectangle, if you will, to this picture. So what I'm doing is I'm taking a rectangular thing here that goes from A to B and T, and S goes from minus epsilon to epsilon. And I'm mapping it to this picture. Okay. And what I'm doing is that at 0, this line, the S equals 0 line, maps to my original curve gamma. They are in the middle. And this whole line at T equals A is like this pinch point. This all gets pinched to stick at P. And everything in this line at B gets pinched to stick at Q. Okay, so that's what these rules tell me I'm doing. I'm taking a smooth mapping of this 2D parameter space, fitting it to gamma straight down the middle. And then if I vary S plus or minus, I'm getting a perturbation of gamma. That's how I'm doing this, getting this perturbation I talked about here, is by going plus or minus some small amount from 0 into S dimension. So if I think about, say, fixing some curve up here, like S is like slightly greater than 0, I'm taking a path that is close to gamma, but it's just a little bit perturbed, but it still fixes the endpoints P and Q. Okay, so I'm only considering curves that start and end at the place I want. And again, if gamma is a length minimizing curve, then any of these curves that correspond to plus or minus an S will be slightly longer than gamma. Okay, right? If I move the curve, and it's the shortest possible curve, perturbing it a little bit will make it longer. And just think of like the straight line, right? If I take a straight line and I perturb it a little bit, just any small perturbation, you of course get a longer curve. Okay. And so what, again, if we're looking for a 0, it's like, your parabola picture, I'm at a minima, then a 0 derivative means that any small perturbation left or right will increase my function value. And that's in this case, is my length. Any perturbation of this curve will move me up the hill. And that means I'm a 0 derivative, a minimum. Okay. So any questions about this setup here? Yeah.
So you said pitch in point P and Q, it means like if we are at point P and Q, then we are only on that point. We're not going to be off from it. Like
that's right. You're saying we'll stay at P.
yeah, it's because I see like there's like on the middle of the curve, like you're like kind of like deviate a little bit from it, right?
Which one here?
Because so I think there's a space around the curve. Seems like it was a little bit deviant.
Yeah, and this point is, yeah, everything meets at P. But if I move up here, I'm still at P. But as I move over this way, then I can come off of gamma like so.
So like so like if we take from like if we take like a positive epsilon,
Yeah,
and then we take any number between A and B,
yeah,
and then like epsilon represent like how much we are like deviate from the curve, like
right, yeah.
like if it was a tangent from
So actually, so one thing you can do here is this is like a slice of a coordinate system, like because this is an n-dimensional manifold, but this looks like a coordinate system like we had, but it's only 2 dimensions, T and S. And yeah, so I think what you're hinting at here is that this coordinate system also has, you know, tangent vectors. And so here, the derivatives of these are just coordinate curves in S and T. The derivatives of those coordinate curves are tangent vectors on this little ribbon variation of gamma I have here. And those are like the perturbations, these vectors, the vector fields, yeah. You can think, and these vector fields, because these things get pinched at P and Q, which I didn't draw super well here. These vector fields shrink to 0 as you get to the endpoints. So, you know, this vector actually collapses to 0 as you get to P and Q. If that helps, yeah. And yeah, the magnitude, and because we have a metric, we can talk about the magnitude of those vectors. And yeah, that tells you how much you're perturbing the curve. Yeah. Does that answer kind of what you were thinking about? Yeah, okay. Other questions, comments? Yeah.
So could I consider just like the geographic coordinate system and P and Q just a 2 pole for the Earth, right?
Sorry,
The P and Q just like 2 pole
yeah, there are 2 fixed points.
at this point.
Yeah, so the coordinates are the S and the T. That's what moves me up and down. So this direction is S. This direction along this little ribbon is T. So think of it just like a little 2D map of coordinates. I can move along S and T. You think of it as this rectangle mapping to this little ribbon. I call it a ribbon with pinched points there. And yeah, I can move along T, takes me from T to Q. And S takes me the variation about gamma, like up and down or left and right, whatever you want to think about it, around gamma. And I should mention, the way I drew it makes it look like, you know, gamma's in the middle and you go up and down. But I mean, this is any possible variation. So these coordinates can actually cross each other. They can, you know, do weird things like this. That's also a valid perturbation if S moves you up and down around gamma is also an acceptable perturbation or variation, because that's still a smooth function, even if it crosses itself and does weird things like that. It's still smooth. It's, you know, got some singularities in it because of the crossing, but that's okay. That's not a requirement here. It just has to be a differentiable function, and it has to fix the endpoints, and at S equals 0, it has to match the gamma curve. But it can do any wild, crazy, you know, thing it wants to do to change gamma in any way you want, as long as it's a smooth change. Okay. All right. So yeah, so that's the variation of gamma. And why do we do that? Because it takes us from this problematic, you know, place we were in where we said if you're in a vector space, you have n dimensions, let's say, and you have to say that in all n dimensions, the derivative is 0. But now we're in infinite dimensions, and I don't want to take an infinite number of derivatives, obviously. But what we've done is we've turned the infinite dimensional space into just a question of 2 dimensions, s and t. Okay, and so we're going to look at the s, the 1 dimension that we've added in our variation, the s dimension. And we're going to say, I can now compute the length of alpha, st, where I'm thinking of alpha st, I really should write it the following way. Fix an s between minus epsilon and epsilon, and then this is just dot, meaning it's a function of t only now, because I've fixed for, this is for some fixed s in minus epsilon to epsilon. This alpha with t variable but s fixed is now a curve, just like gamma was. It's pick an s level and you get a line which corresponds to a curve, and that curve starts at p and ends at q. And so I can compute the length of that curve. There's the camera. I can compute the length of this curve as a curve in t. Okay. So to be super crystal clear, alpha s, I think I'm being crystal clear. You tell me if I'm not. Alpha s dot is a thing that takes t and maps it to the manifold, and it t equals a is at p, t equals b is at q. So this object is a curve from p to q in the manifold. Yeah, so I can compute its length. And what I'm going to do is, because now I can think of this L not as a function of alpha, which is this infinite dimensional thing, but L composed with this is a function of S now. So now I'm going to just vary S, and as a function from S, this is just a function from minus epsilon to epsilon to a real number, a positive real number, in fact. So I can take the derivative of this with respect to S. And then I can evaluate at s equals 0, which is where gamma is at s equals 0. And what I want, if this is a minima, I want this, I will write, I want this equal to 0. That's the condition for gamma to be length minimizing. And now the only caveat here is I want that to be the case for all alpha that satisfy these 3 rules. Any valid variation of gamma, this should be the case. Okay. Now, how does this get us? So this is the condition I need. How does this get us to what we're going to get in the end, or what we're trying to get in the end, is some way to write down an equation for gamma. Like if you give me 2 points in the Euclidean space, I can write down an equation for the straight line between P and Q. So that's what I'm looking for. It's an equation, gamma of T equals something as a function of T. Okay, and the trick is that this condition, if we do some magical calculus here, will give us such an equation in T. That for any manifold with a Riemannian metric, I will get an equation in T. Now, to do that, you can do that directly with this setup, but it turns out it's easier, and this is, I'm going to do some hand waving here. We're going to hand wave and get the final equation without doing some of the gory details. The first gory detail is that instead of doing L directly, because L has this norm, if I come back over here, it has this norm inside here, which is really a square root, right? And the square root is annoying to take derivatives of. It's not too bad, but this makes calculations really ugly. It turns out that you can replace L with the length with something called the energy of the curve, the energy of gamma, which just squares this. So that's the only difference. And very often there's a 1/2 factor here, which doesn't matter. You can put whatever number you want here because I'm just trying to minimize this so you can scale it. It won't change which gamma minimizes it. By the way, this does have a physical analogy. If you know any physics or remember any physics, and you might remember equations that look kind of like this. Energy is 1/2, kinetic energy, I should say. This is specifically kinetic energy of a moving body is 1/2 its mass times its velocity squared. And this is the 1/2. This is the velocity squared. And you might say, well, where's the mass? The mass is in the Riemannian metric. This inner product, remember, has a Riemannian metric here, which is like you can think of as like a multivariate mass of sorts. So anyway, if you actually do physics of moving bodies, you compute kinetic energy that looks exactly like this equation if you just interpret the things we're doing as physical quantities like a mass and a velocity in some constrained space, like a manifold space. So anyway, that's where the word energy comes from, by the way, the letter E and everything. Is it really is like a physical thing in the right context, but for an abstract manifold, it's not necessarily a physical thing. But anyway, so if you do this, the thing that's important for our discussion is that this energy of the curve gamma, if you minimize it meaning minimizing E, you get a gamma, which also minimizes length. So minimizing energy will also do this for you. It's not obvious that that's true. Like it's not obvious because the square's on the inside of the integral, which makes it like, I mean, obviously if the square's on the outside, you could say, okay, yeah, I can see that. But on the inside, it's a little bit non-obvious. So that's why I'm going to leave it as a detail I wave my hand over. I'll make one more remark about that. Notice one thing about the length of a curve is it doesn't matter how fast you travel from P to Q, the length you travel is the same. It also doesn't matter if you start out slow and accelerate and then slow down. You can change your acceleration, your speed rather. You can change your speed as you go from P to Q. Slow down, speed up, and so forth, right? The length doesn't change. The energy does change. If you accelerate or decelerate, you change your energy. So the only difference between minimizing energy and minimizing length is that to minimize energy, you have to, yes, minimize length, but you also have to move at constant speed. You can pick whatever speed you want. I can, move at a really fast speed or really slow speed, but you have to move at a constant speed with no acceleration. Okay, so energy minimizing curves, the things that we're going to call geodesics, the things that minimize this, the gammas that minimize this are called geodesics. They not only minimize length, they also are forced to move at constant speed. Okay. One other thing I was going to mention, and I almost forgot, is that we're doing, this is the calculus trick, find the valley, find the critical point, the zero gradient. And we know that trick, that gradient minimization, doesn't give us global minima always. if my function I'm trying to minimize looks like this, and I do a gradient descent, I land in a minima, and I say, there we go, I'm at a minimum of length. It might be the case that if I went back up and went back down again, I'd find an even shorter curve somewhere else in where I'm searching. Okay, so minimizing this is not necessarily globally convex. So there might be multiple local minima to the geodesic energy equation here. And just to give an example, even though we haven't said what is a geodesic, or I think I've lost the board. Yes, hang on. Sorry, people on Zoom. There we go. So yeah, so I was just saying that we could be at a local minima, and maybe there's a better, shorter curve somewhere else in our space of curves. And I can give an example where that actually happens. You can kind of imagine. You'll have to take it as a word of faith from me that if you're on the sphere, S2, that geodesics are great circles, circles around the sphere, which have also radius 1, the same radius. Like, let's just take the equator for an example here. That is a geodesic. You're going to prove that, or you're going to write down the equations for all this in the next homework. But if I give you 2 points, P and Q, on the equator, then they have this shortest path along the equator, but they also have going the long way around the circle, around the backside of the Earth here, if you will, to get from P to Q. And that's obviously a longer path, but it's also a geodesic, because it locally minimizes length. If I perturb that path just a little bit, in some small perturbation of that path, I'll always get longer. So it is the shortest path I can take without moving all the way around and taking this path instead. It's at least, again, locally minimizing, even though it's not the globally minimizing path. In Euclidean space, you can't do that. You can't find 2 straight lines between 2 points. There's not 2 geodesics between 2 points. On a sphere, there's more than 2 geodesics between 2 points. Another case, of course, would be it's easier to think about the north and south pole here. So 2 antipodal points. I've got this geodesic. I can go around the other side, and it's equally distant. I can take any geodesic, any longitude curve, right, is a great circle. And I've actually got infinite number paths from the North Pole to the South Pole. And same thing, if I took any other antipodal points, I would get equal length geodesics. So there's not a unique geodesic that minimizes length from 2 antipodal points, 2 points that are directly opposite each other on a sphere. Okay, so that you can kind of see how this geodesic minimization, if I'm minimizing length or energy, can result in non-unique minima and also things that are local minima versus global minima. So these are all global minima, they're just not unique. This is a global minima, and this is a local minima, but not a global minima. So you can get these kinds of things happening in manifolds. Okay. Right, so back to, now I'm just going to replace my L with an E. Okay, that's what I'm really going to minimize, is I'm going to toss a square inside the integral there. Yeah, and so to do this, let me just write out, I'm not going to, so this is what I want, but let's write down what this is actually going to look like. This is going to look like dBs, integral from A to B. I'll write out the inner product. The norm is the inner product, alpha S comma T I'm taking, sorry, a derivative in t to get the tangent vector, the velocity of this variation alpha as a curve in t, right? So notice I take d alpha dt. This is my kind of variation. I'm getting tangent vectors in this direction. ddt is in this direction. The s direction is kind of this direction of my thing as I go from P to Q here. But I'm getting velocities of some fixed curve from P to Q here, and taking their dot product. That's the norm squared. Let me integrate that. And then I'm going to evaluate at s equals 0. So there's a ddt inside here. There's a dds on the outside. And I guess I can throw in that 1/2 factor if you want or don't want, doesn't matter. Okay, so this is the part where I really wave my hands and you know, because this derivation would take, you know, a long time to work out completely, carefully, and explain what we're doing at each step. But you can do this with just basic principles of calculus, right? Like I don't need, this is all written down in terms of integrals and derivatives that we know how to write, to argue about. But let me just give the very quick hand wavy thing you're going to do here. We're going to take the s, we're going to bring it inside the t integral, and there's an argument there that that's okay to do. And then I'm going to get, you know, the usual 2 times this times DDS on one side of this kind of thing. Then comes a lot of just manipulation with rules of calculus. And you do an integration by parts in the end. And you get something in the end that looks like an expression times d alpha ds on one side of the inner product with the integration by parts. And then what you say is, because I need this for all alpha, that I can so let me say I'm gonna get this down to something that looks like, you know, integral of something times a d alpha ds. Okay. And what I'm gonna argue here, and that's the part I'm skipping over. But what I'm going to argue here is that because alpha has to be, this has to be true for all possible alpha, that d alpha ds can be anything. And therefore, the something I get here, which I'll tell you what it is in a minute, for this to be true, that this whole thing's equal to 0, this something over here has to be equal to 0. And that something equal to 0 is the geodesic equation. Okay. And this is something called the fundamental theorem of the calculus of variations, that if you get an expression that looks like this, where you have your object is taking a derivative with respect to your variation, our variation is an s, because we have to be all possible variations, this d alpha ds can be basically anything. And so for this whole expression to be 0, because I can plug anything in here, the only way to make this whole thing 0 is to make this thing 0. Okay, that's the logic. So yeah, so there's something equal to 0 is the final expression we get. It's the geodesic equation. And I'm not going to do this because this gets really ugly, the derivation, because remember, what does this actually look like? This dot product is not just a Euclidean, you know, smack your 2 vectors together. This has that G matrix in it. So it's like this thing transposed times the G matrix times this thing. And everything's varying in a coordinate system with the G having x coordinates. And so doing that whole derivation, it gets really ugly, which you'll be able to perhaps guess if you look at the final answer. I'm going to draw on the board here in a minute. To get that final answer, it looks kind of complicated because it is a lot of work to get there, which we can't do in a short 5 to 10 minutes here. Any questions about that last argument about? You know, that if I write this down, I can switch a t and an s derivative using integration by parts, and you just have to take me on faith that I've been rearranged this way. But that fundamental theorem of calculus variations, that if I have some expression here, that this has to be equal to 0 to make, is the only way I can guarantee that for all alpha I'm 0. That's the basic trick.
Does alpha appear in the left side of that?
Say again?
Does alpha appear in the left side of that?
Yeah, this is going to have alphas in it. But then when we evaluate at s equals 0, remember that at s equals 0, so that's s equals 0, this is the same thing as gamma t. So this does have alphas in it, but then we're going to do evaluate at s equals 0, and all those alphas will get converted into gammas.
You never have to worry about instantiating alpha this way.
Exactly. Yeah, exactly. So you never actually have to construct a real alpha. It's really just a tool, a little trick to make all this argument, and then you evaluate s equals 0, and that alpha argument just converts back to a gamma, and now we'll have this equation we'll see is just in terms of gamma, which is what we want. Yeah. Yeah, so it's a neat little trick. And yeah, by the way, I because I'm giving the logic of how this works, but not the gory details. But the gory details, if you go to the class webpage at the bottom, remember I have a link to some notes, or it's kind of like a small textbook by, I think his name's Sigmundur Gudmundsson. I think some Norwegian type name, I'm not sure. Nordic, I should say, Nordic country name. And those notes are on Riemannian geometry, and he has a chapter which does that whole derivation. You can also find it in some like actual physical books that you can find in a library, I assume. There's my favorite is the Do Carmo. It's cited in my short notes. Manfredo Do Carmo Riemannian geometry book has very nice derivation of this. If you want to see the details, if you're into, punishing yourself with math derivations. Okay, so yeah, but for the purposes of this class, understanding where the geodesic equation comes from and the things I just mentioned about it being only a local minimum, that you can get non-unique multiple geodesics like on a sphere, like have that example in mind, and understanding how that all came about and why you can possibly get multiple geodesics because of this local minimization is the important thing. And then having the equation and is going to be important because you're going to actually use it to get a concrete equation on a sphere in the usual spherical coordinates, the longitude, latitude, like theta, phi coordinates on the sphere. You're going to write down that the equator satisfies the geodesic equation. That's the goal of part 1 of the homework. Okay, so yeah, so what is this? This thing equal to 0. Whoops, this kind of makes it look like gamma is equal to 0. Let me just move that. This thing equal to 0, what does that look like? And I'm going to cheat and look at my notes because I will almost certainly make a typo or whatever the chalk equivalent of a typo is if I don't cheat. So so what we get, and oh yeah, let me just notation wise point out the following. Remember, gamma, the output is on is on M. So writing down a concrete equation, I need to be in a coordinate system. So we're still going to have this, coordinate system kind of business here, X, that I'm writing down all these equations in a particular coordinate system. So gamma in the X coordinate system is going to be written as gamma 1 of t, gamma 2 of t, out to gamma n t, okay? Right, because the gamma curve is up here, but if I apply x to it, I can write it just as a curve in 1, 2, 3 at the n coordinates, and that curve will be n functions of t. That's the n-dimensional position of that curve in the coordinate system. Okay. So yeah, so when you see me write a superscript on gamma, it's not a power. Again, this is kind of a notation. The superscripts here will be the coordinate in the x coordinate system. Okay, so the kth coordinate, and this is tricky because now I need a second derivative, so I have a superscript here, which looks like the following. So the second derivative in t of the kth, pick the kth gamma function, it's going to satisfy being equal to the following. Let me write this out. I'll write this out in the full double sum here. Again, let me see how I wrote this in my notes. I think I used this as a function of gamma of e. And now I have first derivatives of the ith coordinate. And that's not a partial derivative, gotta be careful, that's just the t derivative and the j coordinate. So now I need to tell you here what this capital gamma is. It's a set of coefficients called the Christoffel symbols, which I'll define here in a minute. But yeah, so let's think about this equation really quickly. It's saying the second derivative of each of these functions satisfies this complicated thing. It's double summation over taking a product between the first derivatives. And so notice this is a differential equation, an ordinary differential equation. It's an ODE, right? And but it's a nonlinear ODE because I'm multiplying first derivatives together over here. And I should also mention we should also say it's a system of ODEs because there's one of these for every k as k goes from 1 to n. So it's a system of n equations. So it's actually a pretty complicated deal, right? It's not a simple thing. And then to add to the complication, there are these crazy Christoffel symbols. The Christoffel symbols, in the interest of time, I might not write them down. But the Christoffel symbols are going to be this thing that has, again, a sum. There's a sum over another index L. I'll let you, it's in the notes if you want, because you're going to need the equation for these things. And inside of here, what you've got are partial derivatives of the metric. So there are partial derivatives. There's and the other thing that's ugly is there is a inverse of the metric outside. So this thing is really ugly. And we'll get the index right here. Sorry, it's on the inside of the summation. There's a KL. So superscript here means take the inverse of G and then take the KL entry. This is another weird math notation that I apologize, I did not make this up myself. That a superscript means invert the matrix, or a matrix means invert the matrix and then take the KL, entry in the matrix. So there are things like the ith derivative of the L, J, K or something. Anyway, you can look this up. There's like 3 terms here that are derivatives of the G function, the G metric matrix components. And then you have to multiply those things by an entry of the inverse of the G matrix. So these things are really hairy and difficult to compute. But what you're going to find in the homework is that if you think carefully, it's not too bad actually. You write this on a sphere, you can do this. It's going to take a little bit of thinking through what each of these terms mean, but it's in the end, it's not super difficult math in the end when you boil it down. For the sphere, other manifolds can get really nasty, but for the sphere, this is all pretty tractable and not too bad. It looks really daunting, but you can do it not too bad. One thing I'll point out really quickly, I'm sorry, I'm running over time. The metric I said for Euclidean space, G is the identity matrix and it's constant everywhere in space. So these guys are equal to 0 for Euclidean space on Rn. And if these gammas are 0, this whole expression becomes 0. And you get that the second derivative of gamma equals 0. And we know that a line is defined by its second derivative equaling 0. So that's how you get the kind of proof there, if you will, that straight lines are geodesics in Euclidean space, because they are exactly the solutions to the differential equation. Second derivative of gamma equals 0. Okay, all right, thanks.